Wonderful. So thank you all for coming. Bjorn, thank you very much for taking the time for us. Bjorn is one of the absolute world experts in the creation of and application of hydrodynamics, ultra-relativistic viscous hydrodynamics to heavy ion collisions. Bjorn is a scientist in the nuclear theory group at Brookhaven National Lab, working on the theory of nuclear matter under extreme conditions of high temperature and density, and nuclei at high energy. He received his PhD in physics in 2008 from Goethe University in Frankfurt, Germany, and after spending time as a Tomlinson Postdoctoral Fellow at McGill University in Canada, joined Brookhaven in 2010. Bjorn received the DOE Early Career Award in 2014 and is a fellow of the American Physical Society. Just accolades upon accolades and very, very impressive. Thank you very much, Bjorn, for joining us. And you're going to talk to us about fluid dynamics of quark gluon matter in introduction. Please take it away when you're ready.
Okay, yeah, thank you very much for the invitation and the kind introduction. So Will asked me to give these two lectures, and so the first one is going to be really a fairly basic introduction. So I hope I'm not just repeating what all of you already know. So hopefully there's a few new things in there. I know that, for example, last year you heard some lectures on fluid dynamics already. So there might be a little bit of repetition in there. But I hope it's still useful and prepares us well for next week. We're now talk really about the latest results of our calculations and applications to LHC and RIG data, etc., and even looking towards the electron-ion collider, which you may think is a little crazy doing fluid dynamics. But let's start with some history, actually. It's quite interesting, actually, that this year is the 50th anniversary of the Bear Mountain Workshop, which is in New York and happened, in November 1974. And that was a meeting of people who were thinking about what one could do with heavy ion collisions. So one person thinking about it was T.D. Lee, and in this document, he said, in order to study the question of vacuum, so they were wondering of, do we live in a vacuum or in a medium, and what are the properties if you excite the vacuum? We should investigate some bulk phenomena by distributing high energy or nucleon density over a relatively large volume, which is what heavy ion collisions, as we will see, will provide. And so, as I said, this is now 50 years old, so it's actually a nice anniversary and good opportunity to remind you of this. Another thing that says in this document, which is essentially proceedings from this workshop, is relativistic heavy ion interactions will clearly form a field of study interesting in its own right, as well as a particular tool for achieving abnormal conditions of nuclear matter. So that was when they were thinking about, symmetry breaking and things like that, but didn't really quite think of in terms of quarks and gluons yet. So this came around the same time. And then it also says Walter Greiner discusses his latter aspect and on the basis of nuclear hydrodynamics predicts shock wave phenomena and the achievement of high densities. So these weren't really full hydrodynamic calculations, but it was approximate calculations where they kind of described the nuclei that were incoming as fluids and then looked at shock waves that would happen when they collide and had kind of these three fluid pictures, if you will. So that's what they're referring to, a paper that came out also in 1974. One interesting quote that I just wanted to mention because I found it kind of funny is, and they said, we recognized in these problems an ideal opportunity to break conventional divisions and collect together particle and nuclear theorists, astrophysicists, chemists, nuclear and particle experimentalists, accelerator experts, and generally wise men. So that's probably something we wouldn't write anymore 50 years later. But yeah, it speaks to the fact this was 1974 and a kind of interesting thing to say.
Sort of unclear whether the people in the field are wise at this moment in time.
Yeah, that's right. That's right. So yeah, have a look at this document. I put the link, I think, in the first slide here, so you can actually read that. Anyway, so this was 50 years ago. So this kind of really started us thinking about what would happen if we look at bulk properties of the excited vacuum, if you will. So let's look at how we're thinking of doing that. So if you heat up matter, or the vacuum for that point, for that matter, if you just basically take something that has high energy and dump in one way or another that energy into the vacuum, what will happen? So usually we have quarks and gluons confined in protons and neutrons. So if I heat this up, I get some sort of hadron gas. If I heat it up more, I will actually produce mesons that pop out of the vacuum, particle-antiparticle production. And if I keep going, however, eventually I will reach a point where I have a phase transition or a crossover into a new phase of matter, and that's the quark gluon plasma. And in fact, it's essentially QCD that's telling us that this is happening, and lattice QCD calculations actually are able to calculate at what temperature this will happen. I'll come to that. So again, there were really important papers. So there was this Collins and Perry paper, and they said our basic picture then is that matter at densities higher than nuclear consists of a quark soup. And the argument is based on asymptotic freedom, which was awarded the Nobel Prize in 2004. So that's the property of QCD, that the coupling decreases as the energy scale increases, or the distance scale decreases. As the that the coupling decreases as the distance scale decreases. And yeah, so we also in the midst of Nobel Prizes. So again, this is what happened in 20 years ago now. So as I said, from QCD calculations, which we cannot do really with a pen and pens and paper, but can be done on a computer where we discretize the space and have, in this case, for a thermal system, a direction, the fourth direction corresponding to a temperature. They can simulate the system, and they see as you plot the energy density here scaled by T to the 4, versus the temperature, that this quantity increases quite fast in a certain temperature range. And that's, at low temperature, actually, you find pretty good agreement with a hadron gas calculation, which, you don't do in lattice QCD, but you do based on essentially just a calculation of what hadrons you have and what kind of resonances you can form at a given temperature. Now, just the hadron gas calculation would have a limiting temperature, Hagedorn temperature, so you could not actually reach higher temperatures in the hadron gas. So this will just eventually just blow up, and you just produce more and more resonances, and you cannot reach that temperature. However, you see in QCD calculations that you do get over this barrier, and that has to do with the fact that the degrees of freedom change, and you go from hadrons to quarks and gluons. And so this is happening around the temperature of 156 MeV, and that corresponds to something like 1.8 times 10 to the 12 Kelvin. I will compare that to other temperatures so you have a sense of that. So this is telling us something is happening here as I heat up the system, and it looks like the degrees of freedom are changing. So this is a great indication of that we're going from hadron gas to the quark gluon plasma. In experiments, we should be able to, as was already discussed in this Bear Mountain workshop, be able to simulate, or no, actually realize such situations by colliding heavy ions. Currently, that's being done at RIC still for this year, and hopefully some part of next year at BNL in New York, where I am, and also at the LHC at higher energy at CERN. It started at the Beverlec, and then came the AGS at BNL, but I won't go through all the details of the history here. But currently, these are the two colliders where we are doing heavy ion collisions. There's other places with fixed target experiments. We do things at GSI, for example. But yeah, so this is RIC seen from above. We have a 1.2 kilometer diameter ring, and LHC is significantly bigger with 8.6 kilometer. And because of that, it can reach much higher energies, on the order of 20 times higher or so, or more. So this is where we do these collisions. This is a little animation of what's happening at the LHC. So here's a booster where in this case, let's say lead ions go in. We have a proton synchrotron, increasing the energy to 25 GeV. I guess this is actually the numbers for protons. So the numbers for ions per nucleon will be a little lower. So we go through the SPS, the superproton synchrotron, and then into the LHC ring. And here we cross the border from Switzerland to France, I think. And here we follow this lead ion, and this is a picture of the tube as we approach the Atlas detector. And here we see all the components of the detector, and we see the two lead ions colliding. You see a big mess is coming out, many, many thousands of particles produced. And this is how the detector components respond to that. And you see, this is a very complicated thing, and we're gonna be wanting to make sense of what comes out of there, all this big mess, and see what we can learn about the matter produced in that system. Here's some other pictures from Alice in this case. So you see a typical proton-proton collision, looks kind of like this. So these are these little lines are the tracks. You have some forward detectors where you see some particles going that way, but it's not much going on. But if you look at in contrast to a lead collision in the same detector, you know, there's a lot going on, and we have to make sense of all that. And the same for CMS, a proton-proton collision and a heavy ion collision. So a lot more stuff produced. So once again, I told you the temperatures reached are 10 to the 12 Kelvin. So that's about 100,000 times hotter than the sun, center of the sun, or a hydrogen bomb for that matter. So even with a hydrogen bomb, we cannot generate such high temperatures. So we have to resort to heavy ion collisions or something like that. And it's very small. So the size scales of the system that we produce is 10 to the minus 14 meters. So that's about 100 billion times smaller than, you know, the typical water droplet that we describe with fluid dynamics usually. So it's a pretty extreme system. Also, an interesting point, of course, which we always use to explain why this is interesting, but it's not the only reason, obviously, is that the entire universe, right, at some point likely was a quark gluon plasma. So if we really have this picture of having the Big Bang and inflation, then at about 10 microseconds after the Big Bang, we have a situation where we at temperature scales where we should have a quark gluon plasma in the entire universe, right? And then the evolution and expansion leads to the formation of hadrons and eventually nuclei and so on, the light nuclei at least. So this, our understanding of nuclear matter and QCD can be sort of mapped in a phase diagram. Here, it has the two dimensions of temperature on this axis and baryon chemical potential, or net baryon density, so number of baryons minus antibaryons. And this is what we think the structure should be. We don't actually know quite yet. So we know down here from lattice QCD that there is a crossover, so a smooth crossover from the hadron gas to a quark gluon plasma. So this we know from the theory. And as far as we can tell, all the experiments are consistent with that. So the LHC experiment, Rick experiment, we will see are well described by putting in this theory equation of state, which tells us what kind of crossover or transition we have. Other model consideration at higher baryon density, where we cannot directly apply lattice QCD, tell us we should have a first order transition. So if that is true, then there should be a critical point where the crossover turns into a first order phase transition. We have not really directly seen that experimentally. So this is what experimental projects like the Rick Beam Energy Scan are for. So there we're trying to adjust the collision energy and to kind of scan through this diagram. So these little bangs here are supposed to indicate where the starting temperature and biochemical potential is at different energies. So this is higher energy, and as we go to the right, we decreasing the energy. This comes from the fact that, you know, if you decrease the energy, you will not generate so high energy densities, so your temperature will be lower on the one hand. On the other hand, you will stop the protons and neutrons that are coming in the center of the matter that you're producing. And so they will contribute to having more baryons than antibaryons. So the net baryon number or the baryon chemical potential will increase. And so the idea is by doing this energy scan, we should be able to have some going in the crossover range and some in the first order. And so we should, and then the question is what observables will tell us about that? And people are looking at, for example, fluctuations of net proton numbers to pin this down. I won't go into much detail on this, but this is one thing that's going on currently, the analysis of the Rick beam energy scan 2 data. So we want to learn about the properties of nuclear matter at these high densities and temperatures. And another thing that we've learned is that this stuff that we generate there in these collisions behaves like a perfect fluid. So what does that mean? So this was a discovery at RIC, was on the front page of the Scientific American, for example. And the question is, why do we say that? So we concluded this because of certain observables, namely the azimuthal anisotropies in the particle spectra. So these, I will describe what that means, and they're only really well reproduced if we have a system that is strongly interacting, and in particular, so strongly interacting that it's well described by hydrodynamics with a very low, for a system with very low viscosity. And this was confirmed really by results from LHC in 2010 when they did their first heavy ion runs. So what is measured is particle tracks, as I've shown you. And so what we can measure is the direction where these particles are going that are produced and their momenta. So if you look at the momentum distribution of particles, we have on the one hand their absolute value of momentum and the direction where they're going, right? So this is this is the star detector. This is the Phoenix detector. And this is about, let's look at the star one. This is an event display. This is about a 4-meter scale of the detector. What's happening inside, I told you, is like 10 to the minus 14 meter size scale, right? So that's happening in the very center here. And we want to understand the properties of that little blob in the 10 to the minus 14 range, right? That's where really the action happens. And all this stuff that's happening here, and we see in the detector, is much, much later, right? But we try to, from what we see here, reconstruct what's happening in the first, fractions. Very, very small fractions of a second. So how do we get these azimuthal anisotropies? What do I mean by that? So we're looking at, let's say, an angle phi, right? So the azimuthal angle of this distribution of particles. And actually, you couldn't do this really at RIC, but at LHC, you have so many particles that in one event, so one collision, right, of 2 lead ions, we can actually plot the distribution of these guys as a function of phi. Right, so this is one event, one collision, and we see there's some structure to this. And so this structure we want to quantify with a Fourier expansion, right? So the usual thing, and we choose so that this reference angle such that we only have the cosine terms. And what's gonna quantify what this distribution looks like is these coefficient Vn of each cosine n phi term. Right, so we have a constant. First of all, that's just the average number of particles, right? And here I already included the first term also, namely V1. So that's the cosine phi modulation. So you see for this particular event, this is very small. And however, if you look at the second one, you have actually a pretty large contribution. So this is cosine 2 phi. That's what we're going to be calling elliptic flow. And if you go on, you have a third component, a V3, and so on. So this is 4, 5, and 6, I think. And so you can get a very good fit, obviously, to this distribution. And then these quantities are the ones we will be dealing with is V1, V2, V3. Those are our Fourier coefficients, which tell us, the characteristics of or here's even a better one, to higher order characteristics of this momentum distribution. So in practice, you don't really look at one event usually. So you do this as a matter of two-particle correlations. So you take, in fact, two particles from one event, but then you also have mixed events to get the averages out and so on. So there's experimental techniques. So the typical one is two-particle correlations, and you so what you do here is you plot this as a function of differences in phi, that's this azimuthal angle that I talked about between the two particles. So you have a delta phi, the difference between the phi of the two particles. And then you have also another angle, namely the pseudo-rapidity. So that's the angle in the longitudinal direction, if you will. So that's the angle with the beam line. So that's the pseudo-rapidity. So then you take, again, the difference between the eta of the two particles. And that's what you plot here. And you see you have a strong peak at delta eta and delta phi equals 0. So that's just, if you have one particle, it's likely you have another particle right next to it because, it showers, you have resonance decays. All of these happen kind of collinearly or close to the direction where this particle is going. So this peak is understood. Then you have sort of a wayside, namely at delta phi equals pi peak. So that's the back-to-back direction. And what's striking, though, and wasn't quite expected, is that you have a very long range correlation in the rapidity direction. So a particle going this way will be correlated with a particle going that way. And you see, so this delta eta can be 4 or even larger, which is not plotted here. And the correlation remains strong. And the same thing happens actually at the near side. And so if you look at let's look at delta eta equals -4, right? You see the structure, and again, it looks like a cosine 2 phi modulation, reminiscent of what we looked at before, where we had this large V2. So this, again, is a large V2. So why do we get such large V2, and where does it come from? I come to that. I just wanted to mention one thing, that this is a study is similar to what is being done at, with the cosmic microwave background, where we're also looking at these multiple moments and then learn from multiple moments of these temperature fluctuations in the cosmic microwave background about properties, of the universe. So it tells us about Hubble constant and dark matter content and all these things. We, of course, don't have that many points. We can go up to maybe 7, 8, 9 or so. But because we have some viscosity, these are suppressed strongly at high N. I'll come to that. But we still try to learn about the matter that we produce by looking at the spectrum. One more thing to define is centrality. So when we do these collisions, we will have different numbers of particles produced in each collision. If we plot the distribution of how many particles we produce, so this number of charged particles in this case, then the distribution for heavy ions will look something like this. And so this on the right will be coming from central collision. So we expect we produce more particles as the two nuclei overlap more. And so there should be a correlation between the impact parameter, which is the distance between the centers of the two guys that collide. So you think of the screen going into the so think of the beam going into the screen direction, into the screen or out of the screen. And so this is, again, the transverse plane of the collision that we look at. So if the particles don't overlap very much, and then it's sort of a grazing collision, we produce few particles. If they overlap a lot, we have many particles. So one can measure this distribution, and then one can say, the top 0 to 5% events, that's the most central events, and then I can look at observables in classes of the centrality that I give in percent of this entire distribution. So the 5%, 0 to 5% centrality means the top 5% events in multiplicity. So just to clarify this point. So now we want to get to why do we see such a large V2, for example. And so this is a very old measurement from 2001. That was sort of first measurement of elliptic flow by the star collaboration. So if you plot this V2 coefficient, so how much cosine 2 phi modulation we have in the spectrum versus the number of particles, then we see it actually decreases with increasing number of particles. And the interpretation is that coming from what I explained just now, so if I have many particles, I have full overlap. If I have few particles, I have less overlap. And if I have less overlap, then my interaction region where these guys, the geometry of this region where they overlap becomes more elliptical. If they're fully overlapping and our nuclei are roughly round, then I will have basically zero modulation of my shape. And so what this seems to imply is that the initial shape of the initial geometry of the collision is correlated with the final momentum distribution, which is characterized by this V2. So large cosine 2 phi modulation in the initial geometry means large cosine 2 phi modulation in the final particle spectra. And so the interpretation of that is that I have some strong final state effects that are actually able to convert the initial geometry into a final particle spectrum. So the azimuthal momentum anisotropy is generated by a medium response, and that's in the picture of hydrodynamics such that pressure gradients drive expansion. So this is actually a picture from an actual simulation. So you have some initial energy density distribution. It's fluctuating because, well, so you don't have this nice almond shell because, you have fluctuations in the position of nucleons in your incoming nuclei, and you also have color charge fluctuation in this particular model. So you have actually a pretty fine structure. But if you just look at this picture, you see what the hydrodynamics is doing, where you have high density, which is indicated by these lighter blue areas. The stuff in the evolution will flow towards low energy. So the pressure gradients will drive things into the black regions here, right? So you will kind of squeeze stuff out. You see this here. Here was nothing, and now all the stuff is going that way. Well, the same on this side. There's sort of a hole here, and all the stuff is going that direction. So you see the pressure gradients drive the stuff. And so if I had a shape like this, initially I will get a shape that's actually going to be turned around and going the opposite direction. And so this is here a little bit more complicated to see because we have all these fluctuations, but that means we also have all these higher order harmonics there because of the fluctuations. So for example, if I just had a shape like this, it would produce a large V2, which I have here, right? So that's the interpretation. So epsilon 2 here means essentially the V2 of the initial distribution. So that's the Fourier coefficient of the cosine 2 phi modulation of the shape. Okay, so now we want to see if we can, simulate this in detail and actually calculate things like the V2 of charged hadrons. So these are the ingredients that we typically have in such simulations. So we have this whole thing centered around fluid dynamics because we think, oh, okay, we need something that's really efficient at converting this initial shape into final state particle spectra. We have an initial state model that we need because hydrodynamics is an initial value problem. So we need to come up with, how do we describe the initial energy density that's deposited in the system. We will see that hydrodynamics also requires an equation of state that we can get from lattice QCD, as I mentioned. And at the late stages, when the system becomes more dilute, we have to think of something else because hydrodynamics may not really be applicable anymore because it is too dilute and there's not that many strong interaction happening. And we kind of resort to either just freezing things out and let them stream freely or use a microscopic hadron transport model. And then we can, use this to compute bulk properties of the system just by looking at these particle spectra that come out of the simulation. We can also use this to compute more things like high momentum probes, like jets, like how they lose energy in this medium. There additional theory components will be needed, like PQCD calculations or something else. We can look at heavy quarks, electromagnetic probes, like the photons that are emitted from the medium and also before the medium has formed. All these kind of things can help us learn about what's going on in these collisions and learn about the properties of nuclear matter. So I want to start with fluid dynamics. And again, I realize that you've heard like a lecture by Bjoern Schenke, for example, that introduced that, but I'm going to repeat a few of those things. And I hope I won't bore you too much with that. So fluid dynamics, I motivated why we are interested in learning about it. What it means is really to treat an ensemble of particles, as a single fluid. So we compute the particle ensemble's mean velocity at each point in space and time. But doing so will lead us to lose information about the spread of velocities around the mean, right? So we don't know every microscopic velocity anymore. But if we are in local thermodynamic equilibrium, then we know the spread of the velocities, right? That's given by the temperature of the medium at that point. So this local thermodynamic equilibrium requires that we are obviously locally in equilibrium. And that's achieved usually only if the mean free path is much smaller than the length scales, any other length scales of interest. So this may be the size of the system or the length scale on which the energy density typically changes. So length scales of the gradients of the systems or so. So this is what goes into this approximation. So we need, enough interactions, so a short enough mean free path for this to work. And I'll come, of course, to corrections to this that we lead us to, viscous effects, etc. But that's the basic assumption. Now, in the non-relativistic case, and I know most of you have seen this before, we can derive the equations of fluid dynamics. And they come obviously not from microscopic properties of the system, but really from just the basic conservation laws that we have in the system. So in the non-relativistic case, we know mass should be conserved, right? Energy should be conserved, momentum should be conserved. So starting with the conservation of mass, we can actually fairly easily derive the continuity equation. So this is done in this picture. So what we have is just, we take in this example, I just take a cube, right? And so the conservation of mass means that the total mass inside of this cube has to come and is conserved, right? So the change of that mass inside that cube has to come from the mass flowing into and flowing out of the cube, right? So if it changes, some mass has to come from outside or leave the cube. And that's written in this equation, essentially. So d dt of rho times dx, dx1, dx2, dx3, that's the volume, right? And rho is the mass density. So this thing in the brackets is the mass, right, inside of this cube. And that has to come from in and out flow, which is, these terms are indicated here by these arrows. So this, for example, is rho v1. So that's the mass flux. V1 is the one component of the velocity, right? And dx2, dx3 is this area, right? So this tells us how much mass is flowing in given the velocities of the stuff that's moving around. Now, importantly, on the other side, I will have a slightly different flux, and I characterize this by the change of my rho v1 as a function of x1. That's this direction, right? So the stuff, how much flows out is slightly different from how much flows in, and that's indicated by this, derivative times the distance that I take, which is dx1. So this is indicated here. So if I add all these together, right, and take care of the directions, whether it's coming in or going out, then I end up with this equation down here. So this is showing me that, telling me that the change of the mass density with time is given by this equation, which in vector form, right, I can write like this. So this is really just given by this nabla rho v, and that's the continuity equation. There's another way to derive this more formally, right? So for any volume, so we don't have to assume a cube, right? We can write in integral form. This is the change of mass with time, and then this is the stuff that leaves the volume integrated over the surface, right? Then we can use Gauss's theorem and rewrite this volume, the surface integral into a volume integral, right? And we have the same equation in the end, because this should be true for all kinds of volumes of any shape. But essentially what we did in the previous slide, we kind of derived this Gauss's law using a cube. So that's the continuity equation, one of the important conservation equations for fluid dynamics. And another one is the one for the conservation of momentum. And there, essentially, we do the same thing again, right? So instead of mass, now we plug in the momentum density. So, momentum is mass times velocity. So momentum density is rho times velocity. So we replace rho by rho v in all these terms that we had before. But we have to consider one thing, that because essentially these are forces, right? So we're going to look at the change of time of momentum, right? So this thing is essentially a momentum, and the change of momentum with time comes from a force. So these are essentially force units of forces. So we have to, in addition to what we get here on the right-hand side by just replacing rho by rho v, also the force coming from the pressure from outside fluid elements acting on my fluid element that I'm dealing with. So we have this additional term which has the pressure in it. And then Ni is a surface vector, right? So, and I wrote this now here in terms of just components. So these I mean all the three spatial directions. So there's one equation for each of these. And it's a little bit more intuitive to look at the components. So I have, again, the change of momentum density component I, right, is given by this equation, which contains this term, right, which is the same as what we had before, just now with rho vi and written in components. So this is the product of v dot n, the surface vector, the vector perpendicular to the surface that I'm dealing with. And I have a sum over the directions j here. And then I have the pressure, right, acting on the surface I. And again, I can use Gauss's theorem. I can convert these surface integrals into a volume integral. And I end up with this equation. And so you see I have a VI, Vj term here, and that's a tensor, essentially. That's a second rank tensor. And I can now change this a little bit if I want to. So first of all, I say, again, this is independent of the specific volume I'm dealing with. So I can get rid of the volume integrals once again, and I get this equation. And I can modify this equation a little bit by plugging in the previous equation, the continuity equation, which was the one for dt rho, right? So if I expand this, I will have a term vi times dt acting on rho. And then I can plug in what I had for that previously, right? Namely this nabla rho v. And then I can rewrite this a little bit. And that's the Euler equations. So I rewrite this going back from the component writing into the vector, right? So I just combine all I components into this vector again. And so I marked this term in red because that's really the interesting term. You see it's nonlinear in V, in this velocity field. And so that's where all the interesting nonlinearities in hydrodynamics actually come from, right? So I have V times the gradient of V, right? Sorry, the divergence of the vector field, right? So this are the basic equations of fluid dynamics in the of ideal fluid dynamics in the non-relativistic case. So we have one equation that's coming from the conservation of mass. We have three equations coming from momentum conservation. We will not get an extra independent equation for energy conservation. That will be always dependent on this. So we'll end up with just four equations, but we have five unknowns, namely the mass density, the velocity field, and the pressure as well, right? So all of these are not known. So we need one more equation which connects our pressure or expresses the pressure in terms of the mass density in this case. So that's the equation of state. And it's an equilibrium property of the system, right? It's a thermodynamic relation. And the microscopic physics would enter here, right? So the specific form of this equation of state will depend on the underlying theory, right? The microscopic properties of the theory. And we'll come to that when we get back to the QGP, so Quark Gluon plasma, or the nuclear system. Now let's move on to relativistic fluid dynamics. So there we have to make a few changes. So in a relativistic system, you know, mass density is not going to be a good degree of freedom, right? It does not account for the really large kinetic theory that I might have in a system where things are moving around with the speed of light, right? So I can convert energy into mass easily in a relativistic system. So mass is not conserved. So one should replace rho by the total energy, epsilon, right? So that's the first thing we need to change. We cannot use mass as a conserved quantity anymore. Also, a vector v, I should have said, or calling it, yeah, so it's a free vector v or u. It does not transformed correctly, right, under Lorentz transformations. And so if I'm in a relativistic system, right, it's important that my changes of frame, right, are not changing my basic quantities. And so I should convert this vector, free vector, into a Lorentz 4 vector. And that's what I call U mu. And it's defined as this, and mu are the indices, right? So it run from 1 through 3, sorry, from 0 through 3, and 0 is the time component, and then the other 3 are the spatial components. So I have dx mu d tau, and d tau is the proper time increment. And so that's essentially the same as the Lorentz invariant measure or line element. So ds usually. So d tau squared is just my metric. I call it eta mu nu because here I use a flat space. So generally it's g mu nu times d. Yeah. Sorry, was that a question? No, okay. So that's essentially just g mu nu dx mu dx nu. And because of what x is, right? Dx is, we have this can be written as dt squared minus dx vector squared. And this I can rewrite as a dt squared 1 minus dx over dt squared, right? And dx over dt, that's just my my velocity, right? So this thing is essentially this. And mind you, I always set C, K Boltzmann, and H bar to 1, right? So the C in here is always 1. So I repeat this, what I wrote in the previous slide over here. So this is the same thing I wrote before. And so from this, we can get what U mu is, right? So I said U mu is dx mu d tau, and that you can rewrite as dt d tau times dx mu dt. And dt d tau I get from above here, right? So looking at this, using that I can basically manipulate these infinitesimal elements like numbers, right? I can essentially see that I have a 1 over square root 1 minus v squared here in front from the dt d tau, right? So I have to pull this on the other side, take the square root. And then the dx dt is just a vector which has, you know, dt in the first component, that's 1, and then I have v again. And so this prefactor, that's our gamma factor, right? So that is our Lorentz factor, gamma of v. And so that's what u mu is. So in the local rest frame, for example, right, v is 0 and u is just, u mu is 1, 0. And because u mu squared, right, if I just compute that, is gamma squared times 1 minus v squared, right, in the metric I chose, then u squared is just 1, right? So because of this additional condition that's always fulfilled, I actually don't need additional components, right? Even though I went from 3 components, I don't need additional information or constraints, right? I went from 3 components v vector to a 4-component u vector, which I'm going to use as my velocity field. But I don't have to get any more information. It's constrained, right, by this condition. Okay, so now we know what our velocity field should be in the relativistic case. We also want to know what our energy momentum tensor is, right? Because we're going to be dealing with energy conservation, momentum conservation. So we want to know how do we express the energy momentum tensor. So the ideal energy momentum tensor, where we have no viscosity, has to be built from, or can only be built from, the pressure, the energy density, the u mu field, and the metric, right? G mu nu in general. It should be symmetric and transform like a Lorentz tensor, obviously. And so the most general form that we can have is the structure, right? So we have just some arbitrary prefactors. We have it proportional to epsilon in the first term, and then the g mu nu, u mu u nu, and the pressure, and the same g mu nu, u mu u nu. And to constrain what it really should look like, so what we see not through C3R, we can use the constraints that we know from the local rest frame. So when u mu is just 1, 0, 0, 0, then we know the T00 component is the energy density, and the Tij, the rest of the diagonal, is given by the pressure. So plugging these in, and I won't go through the detail, we will get this result, right? So this is our T mu nu in the relativistic system given by energy density, pressure, and the flow velocity. This can be rewritten a little bit, and I'm just going to use this in the next few slides. So you can define a projector which is orthogonal to the space, or is a projector on the space orthogonal to u mu. So that's just a projector that is g mu nu, our metric, minus u mu u nu. And when you plug that in, obviously, this term just becomes a delta. So that's all that is. So I will write it usually something like this. And then if there are no external sources in the system, then this T mu nu should be conserved, and that's quantified by this conservation equation d mu, T mu nu equals 0. You will also see that that makes sense when we look at the next few slides, where I'm going to link that back to what we had in the non-relativistic case. But this is really, in the simplest form, the ideal relativistic hydrodynamic equations, okay, for the energy density and the momentum density. If you want to identify equations that are more in line with what we looked at in the non-relativistic case, where we had the continuity and the Euler equations, you can actually get that out of this d mu T mu nu equals 0 by projecting with two different projectors, one parallel to u mu. That's just this u nu here. So u nu acting on this d mu T mu nu will give you this expression. I won't go through the details, I won't have time, but this will give you an equation of this form, right? So we have a d mu u mu in there. You have this d in there, which is the opposite, this u mu d mu, right? So that's certain derivatives that come out, and you can get the other equations by projecting on the space perpendicular to u mu. And again, we already introduced this projector, right? That was the delta mu nu, that was the g mu nu minus u mu u nu. You act with that, you get another equation, right? And that you already see this has this gradient of pressure in it. So I write pressure now as this capital P. I'm sorry, I had used a small p before. And so this, you can see, is probably equivalent to the Euler equations. And we can actually see this more directly. So if we go back to the non-relativistic limit, so I'm just repeating what I just told you we get by doing these projections. These are the two equations we got in the relativistic case. So what happens when we go back to non-relativistic? So V will be much smaller than 1. So we can expand our gamma factor, right? So this was 1 over 1 square root of 1 minus V squared. So if we expand this for small v, we get 1 plus V squared over 2. So we will use that. And we will use the fact that u mu up here in the right-hand corner, I repeated this, is just this gamma factor times 1, times the vector 1v vector, right? So what we just now need to do is replace these components here, namely d and this nabla, with what we would get in the limit where v is small. So u mu d mu then can be just described as, well, we have 1 times dt, right? That's the 0, 0 component. So that's the dt. And then the other component will give us a v dot lambda. And the rest that we'll have from the fact that we have this other v appearing in here, right? That will be of higher order in v because of this expansion, right? We have a 1 plus v squared. So we only take the 1 of the gamma of v. And so this is what we get for d. And then for this nabla I, we do the same thing. So we plug in the expression for our projector, right? That's gi mu minus ui u mu. And here it's actually simple because because of where this appears in the equation, we only need to take the first order term. And so we're just left with whatever this gi mu gives us here. This term has v's in it, right? Because these are the spatial components. And so this will give us something of higher order in velocity. Okay, so the leading terms then that we get by plugging in the small v expansion are going to be given by these. And another thing, of course, is we will replace epsilon again by rho because the non-relativistic system will be dominated by mass density, right? And the energy density from the kinetic energy can be neglected. And also in a non-relativistic equation of state, usually of state, the pressure is much smaller than the energy density. So I also make this approximation. So essentially the epsilon plus p's here are going to be placed by rho. And then when you do all this, you get back to these equations, which are exactly the ones we derived in the non-relativistic case. So you see this d mu t mu nu indeed contains all the physics of the continuity and Euler equations in the relativistic case, and we can get the limit back in the of the non-relativistic physics that we looked at in the very beginning. Now I want to introduce some viscosities. So what happens if the system is not an ideal fluid, right? So we have to include dissipative effects. And what you can do to do that is just extend our T mu nu to include this ideal part that we already have, plus a pi mu nu term, which is the viscous stress tensor. So just very generally, I just write this as another tensor. And in a system without any conserved charges, so let's say all these chemical potentials like mu b are 0, all the momentum density is due to flow of energy density, right? So basically acting with u mu on t mu nu will just give us epsilon u nu and nothing else. And so this means that u mu acting on this part here, right, has to be 0. And so that's always true if you don't have these charges. If we do, then this corresponds to choosing a specific frame, right, where this energy density is at rest in the frame. So that's the Landau frame usually. Alternative, I could pick a different one where the charge density, if we have this charge density, right, is at rest. And that's usually called the Eckert frame. But we're going to stick with the Landau frame where this holds. And then the equation of motions can be obtained, again, the same way I did by projections of d mu t mu nu of this equation, right, with projectors parallel and perpendicular to u mu. And you see the form of the ideal part kind of remains the same. And then we just have this additional terms involving this viscous stress tensor. And so this complicated looking nabla bracket or parentheses u mu u nu is to indicate a symmetrization, which is actually not necessary, right? Because pi mu nu is already symmetric. But in the end, this will actually be more convenient to write it this way. And from the second law of thermodynamics, right, we can actually determine what this pi mu nu, what the structure of this pi mu nu should be. So the second law of thermodynamics tells us the entropy has to be 0 or increase, right? So in the ideal case, actually, the change of entropy has to be 0 or it has to increase. And so in the ideal case, actually, entropy is conserved, right? But in the viscous case, I can produce entropy through these additional terms. And because I have to produce entropy according to the second law of thermodynamics and not reduce it, I will get a constraint by applying this law, right? And so what I can do is actually, express through thermodynamic relations this entropy with current, which is S mu given by S times U mu, right? If I express this in terms of epsilon and P, I can write this equation in a way involving epsilon plus P and then plug in these equations again. And then that gives me a constraint, or the first equation, I plug that in, and it gives me a constraint on this last term. So from these arguments, I get the fact that pi mu nu times this gradient, symmetrized gradient term, has to be greater or equal to 0. So this gives me a hint on as to the form of what this pi mu nu will look like. Before I write them down, I just want to separate this out a little bit into the two physical situations of shear and bulk viscosity, and that I do by splitting this up into a traceless part. So that's the symmetric traceless part, the little pi mu nu, and the rest, which is essentially proportional to the trace. And this has this projector in it. Okay, so if you define another quantity which has these sort of bracket u nu terms, that's just this to say this is the symmetric part, right, which we had defined before, minus essentially the trace. So this gives us the projection on a symmetric traceless component of this tensor, okay? And then we have this form, right? So this whole thing that we said, because of the second law of thermodynamics, has to be greater or equal to 0. We have this split into these two parts. And you can directly see that this is always fulfilled if pi mu nu is proportional to this quantity itself, right? Because then you have a square and it will be positive. And pi is proportional to minus times some prefactor of this quantity itself again. And so this will be always positive, and the second law of thermodynamics will be fulfilled. And so then we get these forms for shear and bulk viscosity terms. The proportionality constants here are essentially our shear viscosity eta and the bulk viscosity zeta, which need to be greater than or greater or equal to 0. And these, together with what we have here, are the relativistic Navier-Stokes equations. So the first order ones. Before I go into issues with those, just quickly, so shear viscosity that we just defined describes resistance to shear flow, right? So if I move things like this, there will be a force sort of perpendicular to that, and there will be a drag, a resistance to the fluid flowing into that direction. And if I look at these at different layers, I will have this delay of the fluid following that flow, depending on how large my shear viscosity is. And the same thing for bulk viscosity, except that that's a resistance to the expansion, so a volume viscosity, if you will. So if that zeta is large, my system will try to resist this overall isotropic expansion. Now, second order viscous hydrodynamics is necessary because these relativistic Navier-Stokes equations, which are first order, exhibit acausal behavior. So you can look at this in terms of modes. So large K modes will travel faster than light. You can also see directly that there could be an issue, because if you look at what we just derived, namely that this bulk viscous pressure term is directly proportional to the gradients of the velocity field, right? So it will immediately know, right? This dissipative current will be immediately generated once I have a gradient here. And so this can be an issue, for the large K modes of this, and that leads to information traveling faster than light. And so then if things travel faster than light, they can also travel backwards in time, depending on my frame. And then I have no longer an initial value problem, which hydrodynamics should be. So this messes up everything. And it's really a problem also for numerical stability once I plug this into a code and try to solve these equations. So what you would have to have is sort of a delay, right? A so-called relaxation time, where my system needs some time, right, to realize what the gradients are and react to it with these viscous currents. And so this can be done by including viscous corrections to the entropy current that I just described, which is actually what Israel and Stewart did. And then once you have that, and again, employ the second law of thermodynamics, and you get new equations, which are in fact relaxation type equations, which will have a relaxation time, which will delay this response to the gradients. And that leads to the Israel-Stewart equations. It can also be derived from kinetic theory. So you start with the Boltzmann equation, and this can be done nicely systematically there in the kinetic theory by, for example, expanding a system in terms, in the various gradient terms, and then only keeping those that are, leading in inverse Reynolds number and Knudsen number, which are characteristic measures of how close I am to equilibrium. I won't go into the details of this, of course. I don't have time, actually, already over time. So how much time do I have?
As you need at this point.
As I need at this point. Okay. So I try to be fast. I don't want it to keep you too long. But so these are then the DNMR equations, so another second order hydrodynamic equations that are commonly used now in simulation frameworks. So I finished the first part of this. I'm going to quickly just tell you about the other aspects we need to do a simulation. So there's initial conditions. So one can use, for example, smooth initial conditions that don't look like this blob, but are really more like this almond shape that I just showed you briefly in the beginning, like, of these overlapping nuclei. One can get these from optical Glauber models. There's also Monte Carlo Glauber models where one, which is a geometric model where we first determine the positions of nucleons in the incoming nuclei, determine whether they collide or not, and then deposit energy or entropy density at the positions of the wounded nucleons, which are the ones that actually participate in the collision. So there's also this so-called Trento model, which is an implementation of such a model where we have a parameterization of how this energy or entropy density is deposited. And that can depend on, that includes different functional forms of how the thickness functions, which I will define, are used to parameterize the energy density deposited. There's other color glass condensate-based models. So there's, for example, MCKLN. It's not used very much anymore. More used in the CGC is the IP-Glasma model, which is using classical Young-Mills equations for the early time evolution of the gluon fields, and also includes additional fluctuations for particle production coming from the color charge fluctuations in the system. So there you don't deal with nucleons colliding directly anymore, but you first compute sort of gluon fields of the incoming nuclei, and then compute the gluon fields that you create in the collision as two sort of dense gluon field system collide, which are my two heavy ions. And then the time evolution in the very beginning is actually covered by Young-Mills equations, and that can be coupled just by taking the energy momentum tensor that this produces and plugging it into the hydro as initial conditions. There's also AKRT named after the authors. I should put references here. And that's a perturbative QCD-based model that also has a saturation criterion, actually, which determines significantly determines the initial energy density also, which will then be plugged into the hydro. There's also hadronic cascades like UQMD or Nexus, and protonic cascades like the BAMS model from Frankfurt, which can provide initial conditions. Also AMPT, for example, which is based on Haijing, which is based on Pythia. So all these different, there's a big list of models that people have used to provide initial conditions for hydrodynamics. What used to be, or still is in a sense, a very popular model is the Monte Carlo Glauber model, which I mentioned. There you sample, as I said, the nucleons from the nuclear density distribution, which could be a Wood-Saxon distribution or something more sophisticated. You also sample randomly an impact parameter, and you say that once, now I have these two nuclei, I know the impact parameter, and I say a nucleus-nucleus collisions is given as a sequence of independent nucleon-nucleon collisions with the nucleon-nucleon cross-sections. So there, nucleons are assumed to travel on straight line trajectories, and each nucleon-nucleon cross-section is independent of the number of collisions that I totally have. So, and then once I have this determined, so I know now, according to this cross-section, which two nuclei should collide. There's some sampling involved, so some randomness involved too, in some cases. Otherwise, it's just like a fixed size. So if they overlap within the size defined by this cross-section, they will collide. So if they have collided and I've determined that I assign a smooth energy distribution around each nucleon, around each wounded nucleon, and it's usually parameterized as a Gaussian. And then I can also introduce some substructure if I want to. So I could say there's some hotspots inside the nucleons. That's also been very popular. But I'll discuss such a thing in more detail next time. I just wanted to define one thing, which we'll also use next time, which is the thickness function. So that's, I told you, used to parameterize in some models the energy density that I dump in as my initial state, or the entropy density. And that's really just an integral over the longitudinal direction, the beam direction of my three-dimensional nuclear density distribution. So for a nucleus, this could be a Gaussian, it could be a Wood-Saxon distribution like here. I could also actually have a deformation of that nucleus, which is not included in this equation, but I could have that. And so if I integrate this over the longitudinal direction, right, I just have, whatever the other nucleus sees from this density distribution that's encoded in this TA. And in the Monte Carlo Glauber model, this TA is actually constructed from the thickness functions of the individual nucleons, which I assume as Gaussians, integrated over the longitudinal direction, right? And then I have one TA and one TB for the two nuclei, and I can construct the energy density from that. So in the Monte Carlo Glauber model, this would look something like this, right? So I have the view where the beam line goes into the screen, and the the ones that collide in this particular event are darker, and the lighter ones are spectators. And this is the side view, right, where I see the beams coming in and indicated already here which ones will collide because of their position, right, in the Monte Carlo Glauber model. And then the energy density will come from this distribution, which is lumpy, of wounded nucleons. Finally, equation of state. I don't have much time, so just quickly, we use an equation of state typically constructed from lattice QCD. As I told you, in lattice QCD, I can measure the trace anomaly. From thermodynamic relations, I can actually link directly the trace anomaly to the derivative of pressure scaled by t to the 4 here. And so the inverse is possible by doing these integrals over t of the trace anomaly. So this is a way that the lattice QCD people construct the pressure as a function of t. And then again, this can be smoothly matched to a hadron resonance gas around a temperature somewhat below the crossover temperature. And that way we can construct an equation of state that's valid over the entire range of t. Usually the lattice doesn't go down to very low t. So we use a hadron resonance gas model down there. And then recently, people have started to construct also equation of state as non-zero chemical potentials for baryon, strangeness, and electric charge. And now we actually have some equations of state where we have a 4-dimensional equation of state in the space of temperature and these 3 chemical potentials. And so we can really independently evolve all these charges and energy density in the hydrodynamics, which is relevant for the lower energy collisions. The lattice informations on these mu-b's has to be done with some Taylor expansion or something, because I cannot directly solve lattice QCD at finite chemical potential because of the sign problem. But with the expansions done and then some extrapolation, I can construct an equation of state at least within some range of these chemical potentials. Yeah, so this is just examples of what people had used in the past. So how different people have used different lattice data and also differently constructed the matching to the hadron resonance gas. There were some differences, for example, with the older one, S95P, in terms of trace anomaly, and also in terms of speed of sound, which I get from that. So these differences matter somewhat. So for example, if my speed of sound in the equation of state is somewhat lower, right, this would affect how I extract the viscosities of the system. So for example, the VNs, the V1, 2, 3 that I introduced in the beginning would change by 10% if I change the speed of sound like this in this range of temperature. And that means eta over S would have to change by 50%. So it actually makes a difference what I put in for the equation of state. So we're trying to put the best possible extraction from lattice QCD in there usually. Finally, if your hydrodynamics starts to end, usually use something like a Cooper-Frye method, where you assume each cell where the density or temperature drops below a certain value acts as a black body radiator of particles. And so in the case where we want to match the system to a hadron resonance gas simulation, we look at each element of such a freeze-out surface, which is determined by this threshold of energy density or temperature. So if the system drops below this threshold, we'll have a surface element there. And then we say, okay, we produce particles depending on the local temperature and flow velocity. And then we compute the resonances, like all the particles that are possible, right? And feed those distributions or samples distributions in this case into URQMD or SMASH or another hadron cascade, which then performs some scattering still and also the resonance decays. And then we usually look at pions, kaons, and protons, for example, or even higher resonances or more multi-strange particles, and see what they look like. Okay, so this is a simulation. This is the temperature contours of constant temperature in one collision event. The duration of this video, which is repeating over and over, is about 10 Fermi/C. So in reality, this would only take 10 to the minus 23 seconds. But here we can actually watch it. And so this is actually plotted not in in tau eta coordinates, but in t, x, y, z coordinates, right, in the lab frame. So you see the temperature drops quickly here at the center, right? So this becomes kind of the darker blue very quickly. Whereas at the front where this is moving very fast, right? The temperature stays more in this turquoise white regime for longer, right? And that's actually seeing time dilation in action, right? So the stuff that's moving very fast from our point of view evolves much more slowly, right? Temperature drops much more slowly than in the center where it's not moving in the lab frame at all, right? It's kind of sitting still. So the temperature drops very quickly from the lab view. And here, where it's moving very fast, it's dropping very slowly, which is quite interesting. And that's what you get when you convert back into this t, x, y, z coordinates of your system. The simulation is done in a system where, yeah, I kind of take this expansion, longitudinal expansion, convert it into these tau eta coordinates. And so I don't have to worry about that this goes so slow. If I use the TXYZ system, I would need a huge lattice in the Z direction and would have to wait for a very, very long time. So this is why one converts into a coordinate system where this time dilation is sort of taken into account already in the coordinates. And one more thing is the effect of shear viscosity that you can see here. So I told you shear viscosity is sort of trying to resist these shear effects. And so it will kind of try to smooth out things more. And so this left plot will show with the same initial condition as the others, the case for no shear viscosity, so ideal hydro. And then the shear viscosity increases going to the right. And so what you see is the systems evolve and you keep the sharp structures here where we have no shear viscosity, but you see this blurring as we increase the shear viscosity. And this is what you expect, right? So it's a diffusion process. So it just looks like I applied a blurring filter, but this is actually what the hydrodynamic simulation will do as you run it with higher shear viscosity. Yeah, so then you do event by event simulations. You plug in some values for eta over S and for zeta over S, and you try to actually see if you can describe the data. And this is the last thing I want to show. And I go much more into things like this, especially for smaller systems next time. But here I just wanted to close with showing you that we can describe data fairly well over a very wide range of collision energies and systems. So left is RIC, that's the collider at BNL. On the right is LHC at CERN. This is the mean transverse momentum of, in this case, positively charged pions, in this case, all charged hadrons for the different systems. So there's a lot of points, a lot of lines. So focus, for example, here on the Phoenix data for gold. That's the open squares. Actually, you see there's some discrepancy between star and Phoenix, but the error bars overlap, so that's okay. And our results here, after tuning the parameters of shear and bulk viscosity, as I said, lie here. That's the black line for gold. Sorry. And other systems are predicted as well. So you get uranium, the isobars, ruthenium, zirconium, oxygen predictions. Then we have helium-3 gold, deuteron gold, proton gold, and even PP, right? So we're using hydrodynamics in PP collisions, which is something that Landau said we should do a long, long time ago. But of course, the system is very small, and I get to issues maybe with that and applicability of hydrodynamics next time. And here's at LHC. So, we're in the right ballpark of the mean PT prediction. It's not perfect, but, it's very close. Here we actually fit it to RIC, and LHC was a pure prediction. So we didn't tune to this. So this is what comes out as you change the energy by orders of magnitude. This is the V2 for RIC and for LHC, and focusing on here, this where you can see a little bit more. You see over a very wide range, basically 2 orders of magnitude in multiplicity. So how many particles you produce in an event. You can describe this V2 very well in lead and xenon collisions. There's a prediction for oxygen in here in green. And the blue is proton lead. You see our curve is down here, hard to see, but it's a little bit below the data, but it's not too bad for such a small system. But proton is in yellow, and we kind of do not describe that well. So this could be because of the applicability of hydrodynamics, but also could be because of the initial state not being described properly. And this is V3, similar story. This is V24, again, a similar story. So Rick, this is actually very well described. V24 means we're using 4 particle correlations instead of 2 particle correlations. Since I don't have much time, I won't go into detail. But again, one is in the right ballpark. We're kind of not doing as well in xenon correlations here, but overall, as these are really, again, 2 orders of magnitude in multiplicity, this is doing a very good job, which is, what led us in the first place to conclude that we have a strongly coupled system and that hydrodynamic and that we have this almost perfect fluid. This is a differential V2, and I just wanted to close with that much progress has been made. And this is an older plot, but this plot indicates that we've learned about the shear viscosity of these nuclear matter media near the critical temperature a lot once viscous hydro started, right? So from PQCD, we had a very large uncertainty. There's an ADS-CFT limit of 1/4 pi. And then once hydrodynamic simulation started with viscosity around 2007, we were able to constrain this a lot better. And now, well, we already passed this as again, this was an older plot. So now we're learning really about the temperature dependencies and of higher order transport coefficients. And I don't have a conclusion for today because I want to continue next week. And there we'll show you more recent results, right, of hydrodynamic calculations, nuclear collisions, focusing mainly on the small systems because that's really where we're kind of exploring the limits of this and saw the surprise of that, generally the hydrodynamic simulation or strong final state simulations really getting the systematics right, even in these small systems compared to the data. And I will even go to ultra-peripheral collisions to push it as far as I can. So that's basically a photon nucleus collision. And I'll also talk a little bit more about specific initial state models that we're currently using. All right, with that, thank you very much. And sorry for going so long.
Amazing, thank you so much. So opening the floor for questions. Too quickly. I mean, I have tons of questions, but yeah, please. I saw Ben first. I guess Forrest, you also. But Ben, why don't you go first?
So I noticed that a lot of your fundamental equations are all classical in the sense they're relativistic, but classical in the sense that they're not quantum. But would we not expect any quantum effects? I mean, should our fundamental equations not include these quantum effects? Why can we just ignore the quantum effects?
I think the reason that in these simulations you ignore quantum effects because you're dealing with very high densities. And so once you have a lot of stuff, right, you can ignore the quantum effects, which is why we can ignore quantum effects in our everyday life. So these are very highly dense systems where there are quantum fluctuations, but I suppose within the evolution they are averaged out, right? So you could have additional fluctuations like fluctuating hydro, and some of the fluctuations could come from quantum effects. They might have some small effect depending on the fluctuation measure that you use. But I don't, from what I've seen, if you include fluctuations in the hydro, like you also have this fluctuation dissipation theorem and so on, which is not necessarily quantum, but is another way of introducing fluctuations. And on these observables that we usually study, they have a small effect. So I would expect the same on the quantum level. On the other hand, in the initial state, we do have quantum effects, right? So the fluctuations of nucleons and color charges that enter, for example, in the IP plasma, those are essentially coming from quantum effects. But once you've produced the dense system, I think the reason for why they're not so important is that you just have a lot of stuff there and they average out.
And then when you said that we're interested in describing smaller systems, can you still make these approximations?
Yeah, it's a good point. Yeah, so I think once you get down to like just 10 particles, my argument will no longer hold, probably, right? So indeed, yeah, so things get much more complicated as you get much smaller, right? So I think in principle, yes. So you could use, well, I think people use some sort of off-shell kinetic theory, but I don't think they're, too well established. But there is things that could take this into account beyond hydrodynamics, right? So yeah, once you get to very small systems, this is something to really seriously consider. I agree.
Maybe just following up on that. So, I mean, even with macroscopic systems, sometimes quantum effects persist, right? So I'm thinking phase transitions in particular, right? If you're looking for anomalous scaling, that's I mean, that's really isn't it? It's a quantum effect that is in some macroscopic system. So
Yeah.
while I want to agree with you, is there some way that we can systematically be sure that quantum effects are not there?
I think things like that, I suppose you would sort of effectively include, right? Through, well, I don't know, through the equation of state or things like that. But I mean, it's something that's dependent on the microscopic details of your system, right? In hydrodynamics, I think there's no other way. You can only include it through properties that are either in the equation of state or in your transport coefficients, right? So also the transport coefficient could be affected by this, like the bulk viscosity, right? But the hydro equations, in principle cannot be affected, right? Because they're just based on the conservation laws. You could, as I said earlier, include some, fluctuations or so on top of that, going beyond the usual hydro framework. But within the hydro framework, I think the only way to include this is through, modifications of your parameters that you plug in and the equation of state.
Okay, very good. Were you, far as pointing out the chat?
Yeah.
Okay, yeah, maybe let's do the wait, we lost our technology. Let's see what we got here. So we're gonna. All right, here we go. So wonderful PhD student Lorato asks, one, can you discuss how the interplay between fluid dynamics and electromagnetic fields affect charge separation and current formation in quark gluon matter? And then two, this might have been highlighted and I may have missed it, but what conditions force us to impose a non-relativistic equation of state where P is much less than S, and assuming that energy density is dominated by mass density? Oh, that was the non-relativistic limit of the relativistic equations, making sure that mapped on. But yes, maybe the first question, the interplay between fluid dynamics and electromagnetic fields and how that affects charge separation and current formation.
Okay, well, this is probably a long topic, but in terms of describing the interplay, right, you would need something like magnetohydrodynamics, right, which also includes in the equations the effects of electromagnetic fields. I know people have within our field also written some magnetohydrodynamic codes. Usually they're used in plasma physics, right? So if you want to know how the stuff moves around in a tokamak or like a fusion reactor, then that's what you use, magnetohydrodynamics. But they've been also used in the heavy ion field. And then this will tell you indeed how the charges, so you will have to have equations in your hydrodynamics for the conserved charges, right? Which I didn't really address directly, but you'll have one for net baryon number, you'll have one for net electric charge, and also net strangeness in principle. And then you'll have contributions from the external fields, right? So indeed, in heavy ion collisions, right, you generate large magnetic fields because you have large, highly charged ions coming in, moving at very high velocity. So that's a current, and that makes a magnetic field. They come from both sides, so you'll have the two magnetic fields that are kind of, in the azimuthal direction. You have them overlap. So in the overlap region, you have a strong magnetic field pointing in one direction from both nuclei. And then you can couple this magnetic field to your hydrodynamic equation, and you can see how the charges in the system are affected by that. With what I have, I can't do that because I don't have magnetic hydrodynamics, but in principle, that's being looked at. And then you can look at things like charge separation from the chiral magnetic effect, right? So where actually charges are transported along or opposite to the direction of the magnetic field, right? Which is coming from this anomaly that people want to find, namely this chiral magnetic effect through the chiral magnetic effect. So yeah, I don't know if that answers the question, but indeed that's something that can be done and has been looked at. I don't know exactly all the details, but you would need hydrodynamics with the electromagnetic fields included, right? Which exists, right? Unfortunately, one hasn't really found the chiral magnetic effect, but because it's very hard to measure. But yeah, such effects have been looked at in the simulations, indeed. I hope this answers this to some degree. And let's see the second question. Let me see. Let me have missed. What conditions force us to impose a non-relativistic equation of state where? Well, nothing forces us. This was just in the limit, right, of non-relativistic. Is that, I'm not sure if that's what you mean, but in the limit of where I wanted to go back to the limit of non-relativistic equations, right? I said, okay, there we should use a non-relativistic equation of state. In general, we don't, of course, right? So in general, we use, we can use whatever equation of state we want. And here we typically use the one that we get from lattice QCD, right? Is that the question?
No follow-up for the moment, so I think that was great. Thank you. Cole, I think, had a question.
Yeah, at some point you said to get the equation of state, you use lattice QCD, and then there's some sort of process where you connect that to a hadron resonance gas. And I think the end of it was you said that, kind of depending on how you did this, it seemed like you got different answers and different extracted values for either of S. Is this sort of like just people didn't do it correctly originally and now we're doing it better? Or is it like this is a very large systematic theoretical uncertainty? And is this taken into account for the sort of either of S extractions that I've seen?
Right. So I think the main difference here came from the fact that this green line was sort of older lattice data. So which means maybe I think the continuum extrapolation wasn't quite perfect yet or so. And so the more recent ones, which are HotQCD, Wuppertal, and Budapest, and I think there's even more recent ones now. I just had this somewhat older plot still there, which nicely showed the difference. So I took that one. But now the discrepancies are much smaller if you take the latest lattice data from HotQCD and the Wuppertal Budapest group. So large differences, I think the main difference here comes not so much from the construction, but from the difference in lattice data, but also the construction, plays somewhat of a role. But I think now with the lattice data, so I think now this is not a big issue anymore with the latest results. So I think if you look at the latest equation of state, and there's still different ones, they agree much better. So I think this is not a big issue anymore for extracting the viscosity, say. So even here, right? So the speed of sound between the blue and red one, which are the more recent ones, is minimal, right? So I think there's other uncertainties like your initial state and so on, which plays a bigger role in this difference anymore.
Thanks.
Super. Other questions?
Yeah, just quickly about bringing finite density, right, or finite in your phase diagram. How far can they go by now? I've lost track what lattice QCD can do in terms of extending your equation of state.
I think confidently, I think it goes to mu b over t of maybe 3, something like that. So it can go fairly, maybe 2, I'm not sure, or 2.5, somewhere in that range. With various extrapolation techniques. I think typically a hotkey CD is using the Taylor expansion, right? So then for that they get, they say you can go this far, and then if we apply this in hydrodynamics, I think we still need to extrapolate somewhat further, right? Because when we have an initial state for kind of low energy collisions and we have fluctuations, we may run into points in our volume where we have a high baryon density, but not such a large temperature, right? So if you just stop one baryon somewhere, but it's somewhere in a regime where the temperature is kind of low, you still have to have something in your equational state that lets you run your code. Typically, it doesn't matter too much because if the temperature is very low, then you're kind of outside the freeze-out surface anyways, and doesn't really affect your evolution very much. But I think it was 3. Maybe I'm lying, but I thought you basically, some of them say you can go to mu b over t of 3 most recently.
That's way further in than I remember them being able to go.
That's very impressive, yeah. No. Good. Maybe a chair's prerogative, if you're willing to give me some more time. So it was interesting when you went through the finding the equations of motion with the T mu nu. It felt surprisingly ad hoc. I'm sort of teaching first year physics, and I keep insisting to the students that they need to have a Lagrangian formulation, and then from the Lagrangian you figure out your conserved quantities, and it's very algorithmic from Nutter. So it feels interesting or strange that in hydrodynamics it seems so much more, well, it sort of can be some combination. We know it has to be a combination of these things, and just by going to a particular frame that fixes our constants. It doesn't feel as rigorous. So I wonder if you have a thought or a comment on that.
I mean, I think it's using the most fundamental physics assumption, right, of conservation of energy and momentum. So I don't know how much more rigorous you can actually be than only using that. But I think you're referring mainly to the relativistic case, I guess.
Yeah. So I guess, so what's your Lagrangian, and maybe that's not a fair question, or it's not a well-defined question for something like this.
Every Lagrangian makes a T mu nu, right? But whatever it is, you stick in.
Yeah, but the T mu nu looks different depending on the Lagrangian.
Well, if I use Lagrangian or Hamiltonian, right, it doesn't matter, right? I can use either, and Hamiltonian is more in the sense of the, energy, an energy conservation picture. So I think it's in principle equivalent, right? Whether I start from here or from a Lagrangian. So usually people won't use the Lagrangian formulation here, but in principle you could, I guess. I don't see why not. But I cannot write it down right now for you, but one could probably.
No, that's okay. Okay, so then unrelated. So you were very honest in sharing that your calculations don't describe the proton-proton data currently. Have recollections that Romachka in the one fluid to rule them all paper claimed to get the large systems AA, the intermediate PA systems, and even the proton-proton systems. So what's the difference between what you're seeing and what they saw?
I mean, I assume it has to do with the initial state, because you can do a lot of things, right, in terms of the proton-proton initial state. Because, what do? Maybe you have fluctuations inside the proton. If you don't constrain this from anywhere else, you can do anything, right? You can get any shape, any size, right? So Well, maybe not any size if you say the proton has to be the same size as your nucleon size, right, in the nucleus. So we constrained sort of the proton properties, including its size and substructure from Hera data. So that's EP collisions, right? And so there's J-psi production. So diffractive J-psi production is sensitive to the size of the target. And incoherent diffractive J-psi production actually is sensitive to fluctuations of the scattering amplitude, which is related to, or includes fluctuations of the geometry of the target. So with that, we were able to constrain the average size of the proton and the average, and the fluctuations of the structure. And I'm saying this because, so this is really kind of at the high energy, or, that we're also probing at Hera. It's mainly the gluon distribution, right? Which also in heavy ion collisions or proton-proton collisions at high energy is what should matter most, right? Because we're at high energy probing the small x content of the proton. So it's not the charge radius necessarily, but it's the radius of how the gluons or the mass distribution of the proton. And that's actually a little bit smaller. Anyway, so what I'm trying to say is that we constrained the properties of the proton that we put into these calculations by some completely different experiment, namely the EP collisions, diffractive J-psi production. And so we are constrained somewhat in what we can do and play with the proton properties by imposing this on us. And I think if you don't do that, then you can get anything, right, in PP collision. You can plug in any substructure you want. And if you don't care if it's consistent with any other experiment, then I think you can get PP more easily, right? So the main difference, I think, is the initial state that it's been used. The hydros should be equivalent, even though also there's some sonic and supersonic results. And the difference, in my understanding, is the initial state flow. So what they can do is, before the hydrodynamic starts, which is at some time tau 0, which usually is like, 0.4 Fermi over C, or maybe some factor 2 smaller or larger. But then you can either just have the system sit there for that long and do nothing, or you can have some free streaming. And I think that's the difference between sonic and supersonic, whether they have included some initial flow. In their case, I think motivated by what ADS-CFT calculations give you. And then again, they get different results for one or the other. And I think one of them works for all systems, and the other one might not.
But I think following up on that, as we asked in the chat, how should we constrain the initial conditions for hydro?
Yeah, so I mean, this is one way, right, to do that using something completely different. Of course, it may not correspond to the exactly same situation, right? This experiment in EP. I mean, do we really probe the same quantities or the same size that's relevant as a size input in the hydro? I mean, our assumption is that it is. Alternatively, you can try within heavy ion collisions or smaller system collisions to find observables that are not sensitive to the details of the hydro medium, like the shear viscosity or bulk viscosity or equational state, but are more or only sensitive to the initial state parameters. So you can find that out, by just testing in the simulation, right? If I change something in my medium, are these certain observables unaffected? And if I change something in my initial state, are they affected? So if you find one like that, and we have some observables like that, you can use the hydrodynamic, you can use the heavy ion collision data itself, right, to constrain the initial state. So there's these two ways, I guess. And otherwise, yeah, it's just from theory as well, right? But the theory is very, you cannot really do it from first principles, right? You can do like a CGC calculation like the IP Glasma, but it's not fully CGC, right? It's CGC plus a model for the geometry, right? Which is the most important here. So it's really mostly modeling. So you have to have some experimental constraints because the geometry mainly is a non-perturbative effect, right? It's going into the infrared. It's long distance scales often, right? And you have to deal with whether you have any tails that you have to, and confinement effects, right? They affect how the geometry looks. And so it's hard to calculate from first principles, so you have to have some experimental input.
Super.
I have another one on your initial state distributions that you've shown, right, for your collisions.
Mhm.
I seem to remember Javier Albacete at some point when he did when he predicted the multiplicities using using GymWalk essentially from here to LHC, and showed me some pictures of what his incoming nuclei looked like. I mean, they look absolutely crazy. You create more holes, way higher densities in places than what I see you showing me here in these pictures. Do you have a comment on this?
It probably has to do in part. I mean, okay, there's different aspects to it, I suppose. So these look a little bit less crazy because they're already evolved, I believe, to the initial hydro time. So that will already smear this out somewhat. Indeed, if you have, I don't know if you have a picture of this. I don't think so right now. So indeed, if you have if you look at color charge fluctuations and a model like an MV model, right, that essentially is just Gaussian correlations, and you sample color charges in every lattice spacing or so, then you get very large spikes. But these are somewhat, to some degree, lattice artifacts, which will also go away with time as you evolve. So it could be that if you you know, just sample color charges from a color charge distribution that's given by your Wood-Saxon distribution or so, and then look at that, you will have very spiky distributions. But also, especially if you look at time equals 0 or 0 plus or so. So maybe that's what he looked at. I'm not sure. And even if you do GymWalk, that will also kind of smear it out somewhat, right? Because of the small x evolution, kind of, you know, spreading out also the nucleus or the proton as you evolve. You have some Gribov diffusion, things like that, right? So you have some growth of this, and so yeah, I don't know. I mean, it depends on the details of the implementation also. So also the color charge density distributions could fluctuate itself, and could fluctuate more or less depending on what you plug in. So I'm not entirely sure what the differences to that particular plots are.
You're giving me is this well, smears out very quickly.
It smears out very quickly. So I don't know if I have I had a plot like that. I'm not sure if I have it in the backup. This is all. So here's another. So this is actually using GymWalk. I don't know if you. So this is for. Let me just quickly check. Is this helium-3 or something? Or I think this is. Yeah, this is helium-3, right? So so this is. So this is very large and very many holes, right?
But that's only holes.
Yeah, there's only holes, right? Because it's only 3 nucleons, right? And then substructure to that. So it's a very funny situation where you actually have kind of distinct blobs, right? But yeah, as you evolve this with GymWalk, which we did here actually as well, this kind of spreads out a bit and so on. But you have very fine structures indeed, right? And I don't know at what this is, I think at the very initial time. And this is actually not energy density, but it's just a trace over Wilson lines. So it's not even a gauge invariant thing, but it's something that tells you, you know, where is there some stuff and where is not. So it's kind of a representation of what the gluon density is. But it's not a perfect representation. Anyways, so yeah, you could get things like this. And even in a nucleus, you could have some holes, right? If there's no,
Yeah.
by chance, you don't have a nucleon right there. Yeah.
Good. We have another question.
I have a procedural question. On your plots, when you're comparing against the collider experiments,
Mhm.
I was just I was going to ask if you take the fluid, the plasma, and then hadronize it and then freeze stream it towards the detectors. But I saw in your plots you have V on the y-axis. Yeah. So I was asking how long after the collision do you start taking data to compare against collider experiments? Are you constrained by, I don't know, the reconstruction time of, let's say, the LHC?
No, so what we do here is so the system freezes out, right? And I mentioned we calculate particle spectra using the Cooper-Frye formula, and then we sample those spectra, and then we plug them into the hadronic transport, and then that takes care of the final resonance decays and also some final interactions that may still happen. Eventually, nothing will happen anymore, right? And then at that point, the time doesn't matter, right? So as it's called, that's kinetic freeze out. So it's frozen out. That means the momenta don't change anymore. And what the experiments report, right, they are essentially just particle species and momentum, right? Not position, right? We don't care about where they are at these 4-meter detectors, right? So once we know the final momentum, once it doesn't change anymore, and we know the final stable particles, right, that won't decay anymore, then we're done, right? So as long as we see the momenta don't change anymore, we're done, right? And then we just characterize this, for example, the V2, right? As I said, is just a feature of the momentum distribution, right? Not the spatial distribution of where the particles are. So the time doesn't matter anymore. It's just, this is the momentum. That's what they have in the final state. And that's what they will have, once reconstructed 4 meters away or, 1 meter away or whatever in the detector, right? So we just compare momenta and momentum distributions of particles. So it doesn't matter whether it takes a microsecond or however long, right, in the detector. Is that what you mean?
Yeah.
Okay.
Cool.
Oh, one question. So in everything you've been doing, it looks like you are assuming zero baryon density, right?
Yeah, so in LHC collisions and at the top RIC energies, we do assume 0 net baryon density. That's right. So in these plots, yes.
Yeah, I'm just curious, like experimentally, how accurate is that?
So at
Obviously-
LHC, it's a very good approximation. So at mid rapidity at LHC, it's very close to 0, right? Because you produce so many particle antiparticles that whatever, and you stop very little because you have such high energy. So most of the incoming baryons, they will go forward. And even if they were stopped, you produce so much stuff that it would be still negligible compared to the amount of particle antiparticles that you produce. But at lower energies, at RIC, right, you will have to start taking this into account. So at 200 GeV, I think it's still fairly low. I don't know the numbers. But obviously, as you decrease the collision energy, so as you go to 64, 19 or so, or even 7 GeV at RIC, you certainly have a very large, actually, net baryon density around mid rapidity. And there we do take it into account, in fact. So we have some models, initial state models, that can, model how the baryons are stopped, how the protons and neutrons that come in are stopped, and what your net baryon distribution as a function of rapidity is, and also as a function of transverse direction, just like the energy density distribution. And then we can transport it, in the hydro independently, also with this equation of state that takes care of the mu b. Yeah, so if you're interested in things like net proton distributions or stuff like that, then and even just the proton distribution by itself, this will become important at lower energies. And LHC is really negligible. Unless you go to very forward rapidities, right? So if you go to rapidities where you get into the range where, you know, close to the beam rapidity, then it will become important as well. But usually there's no acceptance at beam rapidity in the LHC experiments.
But I wonder, what was it? Phobos had those very high forward measurements at RIC, and maybe there's some interesting physics that they could have measured in terms of hydroflow with large baryon chemical potential.
Yeah, I mean, even now, right? I mean, the beam energy scan star can do that, right? So even there at mid rapidity. So for Phobos, yeah, I suppose they could, yeah, could have. But yeah, I mean, either large rapidity or small beam energy at mid rapidity, right, will make that an important aspect. Yeah. I don't know if there's Phobos data of like, I mean, there's some flow data, certainly. There's even flow as a function of rapidity, I think. But it's very hard to compare to because of the way it was measured. So, right, I think it's using some sort of like just reaction plane and things like that. So, but and I don't know if there's rapidity gaps. There must be in a way, but so it's like, you know, it was the early days and then people didn't really use the techniques that they're using now with like multi-particle correlations and so on. So it's a little bit murky sometimes even what they did if you can't find someone who did it. But because they didn't describe it like, you know, they said, oh, we measure V2, and usually it was like some sort of reaction plane measurement, right? Whether you know, whatever you used, like maybe some forward going neutrons to determine that plane, or right. And I don't know if non-flow was taken care of in the same sophisticated way as they do now, right? Like short range correlations that can mess up the V2 coming from resonance decays or so. So it's a little hard to compare to that old data actually. Because a V2 is not a V2, right? V22 is quite different from V24, for example, right? And then it might depend on the rapidity gap they use in for V22, depending on the system. And so it gets pretty tricky. And if they didn't report it in much detail what exactly they did, it's very hard to compare to this old data. If it exists, I don't know. At very forward rapidity, right?
Right.
Well, I don't want to hold you up.
Yeah. Cool. Well, yeah. So Bjoern, you actually, I think, you have the record for the longest talk in terms of.
Oh no.
No, you've given us a lot of your time. We really appreciate it. So thank you very much.
Yeah, thank you. And well, I hope I won't break the record next week. So